Now let's move on with spin and have some practical examples, the practical experiments that are being performed for the identification of spin. And proceeding from the previous video, I think the very classic example of how spin works in quantum mechanics is what's called as Stern-Gerlach experiment. Stern-Gerlach experiment. I will not draw its diagram because it's quite simple to understand this experiment. And what happens in this experiment is that you have a beam of silver, probably silver atoms. You have the beam of silver atoms, and each with one unpaired electron. So we have He plus atoms. They have lost one electron, and this beam of silver atoms is it's passed through inhomogeneous, or we may call it a non-uniform magnetic field, and so there is a magnetic field, and that magnetic field is non-uniform, and the magnetic moment of this electron interacts with the magnetic field, and there is splitting of this beam. We have a beam in the upper side, say for example, and a beam in the lower side. So this beam splits into the two corresponding to the two possible spin states. So this beam splitting leads to spin states as assuming along z direction. So this s z is h bar by 2. This is for, say, spin up, and sz is minus h bar by 2. This is for spin down. Now, if we think in terms of the Hamiltonian for the spin-half particles in magnetic field, and what's generally known as Zeeman interaction, as we all understand, that then this Hamiltonian operator is negative times mu dot b. So this is the Hamiltonian, and boiling down to minus g mu b s dot b. And g is the well-known Land-Agee splitting factor. Mu b is Bohr magneton. So this mu b is Bohr magneton. And then we have spin angular momentum dot the magnetic field that's there. So this S is basically, it's a spin operator. This S is spin operator. I should keep a cap on it. It's a spin operator. So the magnetic field is aligned along the z direction, and we have the Hamiltonian in the z direction as minus g mu b bz and sz. All right, and and the energy, the exchange energy, is given by g mu b and bz. So this is the experimental outcome, and we have written down its Hamiltonian, and assuming that that the magnetic field is applied in the z direction. So now From here, we'll move to the rotations and these spinors that I talked about. So what's quite fascinating here is, so let's go on with rotations and spinors. And what's so exciting about these spinors, I mean these spins, and one of the fascinating aspect of spinors is how they transform under rotation, how they transform when you rotate them under rotation. Now, if we take the common classical view and if we rotate a classical vector, suppose we have a classical vector and we will rotate it by 360 degree, it's going to come back to its original position. But that's not the case with that's not the case with when you rotate the spin of the particle. That's not the case, and this particle that's represented by this spinor. Uh, uh, now it's this spinor actually changes sign only when you rotate it. When you rotate it, when you rotate it by 720 degree, and that means only after a 720 degree of rotation does it return to its original state. So this is not that we cannot geometrically talk about it because it's made of complex functions. So coming back mathematically to its original position, the spinor takes 720 degree angle to retain its original state. Now, this is deeply quantum mechanical effect, and certainly it does highlight the fundamental difference between the spin, the classical spin, and the quantum spin. Now, mathematically, if we think mathematically, these spinors they transform, and they transform under rotation. And according to unitary representations of the rotation group, if we take the rotation group of SU of 2. Now, so what am I saying is that these spinors transform, they transform under rotations according to the unitary representation of the rotation group, and that can be mathematically written down as R of theta and cap equals exp minus I theta by 2, then spin operator dot n cap. Now, to move on from here, what am I trying is, let's go back to the Stern-Gerlach. I mean, in Stern-Gerlach experiment, we have a beam of silver atoms, and which have unpaired electrons. They are passed through an inhomogeneous magnetic field along some z direction, and what are the possible outcomes of measuring this spin projection along this z-axis, and what's the probability of each outcome if the electron is initially in some superposition state. So let's go on with that, and let's define a state psi. And when we write down the superposed state for this psi, that's 1 by under root 2 of spin up plus spin down. Now, the spin state of the electron is given as the superposition of the spin up and spin down. So what we expect here is the possible outcome of the spin measurement along z-axis are they have to be plus h bar by 2, and this is for spin up, and minus h bar by 2, this is for spin down. Now, to find the probability of each outcome, what we do is we calculate the squared magnitude of the projection state psi onto each eigenstate of Sz. So measuring the probability, so if I have Sz is plus h by 2 for spin up, that's described over here, then the probability of having spin up will be given by the probability density. So that will be the state, the spin up state on psi whole square. So what is it going to give us? It's going to give us 1 by under root 2 whole square. So that's going to be equal to 1 by 2. Now this is the probability of finding the spin up state. Now, in the similar fashion, we can go for the probability of measuring Sz in the negative direction. So measuring Sz as minus h bar by 2, what we call as spin down. So in this case, if I take p arrow down, so that's going to be the mod of spin down state psi whole square. So what will be that? That will be 1 by under root 2 whole square. That will be 1 by 2. So what do we obtain here is as it is expected. Thus the probabilities of measuring the sign, the spin up and the spin down, are both 1 by 2. This makes sense because the initial state is in an equal superposition of the two spin states, and that's what makes it beautiful. And what can be concluded in this experiment is that the beam splits into two parts with equal intensity corresponding to spin up and spin down along some arbitrary z axis, with each outcome having a probability equal to 1 by 2. Now, taking another case, so here we have taken into account Stern-Gerlach experiment, and now moving on from here, if we go with spin and the magnetic field, applying the magnetic field on the spin and trying to understand the interaction between the two. So what am I trying to tell is, we'll go with spin precession and magnetic field. Now, if I consider an electron in magnetic field along some z direction, the electron's spin is it's initially aligned, say, along x-axis. Now, what's the time evolution of the spin state, and what are the probabilities of measuring the spin up and spin down along this z direction? So we have an electron in a magnetic field directed along the z axis, and the electron's spin is to be considered initially aligned along x direction. So we will be looking for the time evolution of the spin state of this system, and what will be the probabilities of measuring spin up and spin down with respect to the z-axis at that time. Now, if we write down the Hamiltonian, so what will be Hamiltonian for this system will be minus gamma S, Z, and B. Well, this gamma, as we understand from our classes, is it's called a gyromagnetic ratio. Gyromagnetic ratio, and it's probably E by 2m. So we don't want to go there. Now we have some initial state. Okay, the initial state of the electron is aligned along the x-axis, assuming to be along x. Okay, which can be written in as a superposition of z-axis eigenstates. Okay, so we can, if we choose, say, some state psi of 0, and this initial state is going to be 1 by under root of spin up, ket of spin up plus ket of spin down. Okay, the superposed state. Now the time evolution of this spin state. Now the time evolution of the spin state will be governed by what? The time evolution will be governed by Schrodinger's time-dependent wave equation. So, so if we think in terms of the time evolution of the spin state, so if I think in terms of the time evolution of spin state, okay, so the time evolution of the spin state is going to be governed by the time-dependent Schrodinger wave equation. So what is time-dependent Schrodinger's equation is the state psi equals e to the power of minus I h cap t by h bar and psi of 0. Now the Hamiltonian is proportional to SC. So it will cause the spin to precess, because this Hamiltonian is proportional to the magnetic field, to the spin angular momentum along the z. So it will cause the spin to precess around that z axis. It will cause it to precess along the z axis. And the eigenstate of SZ will evolve as, if I take the spin up state, so it will evolve as e to the power of minus I omega t by 2 spin up. And spin down will e to the power of I omega t by 2 spin down. Thus, what we have the state at time t. So I can think of the state at time t, which will certainly be a superposed state. So my state will be, the state psi of t will be 1 by under root 2 of e to the power of minus I omega t by 2 spin up, okay, plus e to the power of I omega t by 2 and then spin down. This will be the result, right? So so the probability of measuring the spin along the z direction, so what would be thought along that z axis? Now, in order to find the probability of measuring spin up or spin down along z axis, the project that we have, what we do is we project this state psi onto the eigenstates of SZ. So what's that? SZ is plus h bar by 2 for spin up, and it is minus h bar by 2 for spin down. So if I have to write down the probability of spin up at that time, that's going to be the mod of scat of this spin up psi of t whole square. All right, so what's that going to be equal to? Because this is spin up, that's going to be 1 by under root 2 e to the power of minus I omega t by 2 mod of whole square. So since we understand this mod of whole square is the representative of the complex and it's the product of complex function and its complex conjugate. When you will multiply the complex conjugate of e to the power of minus I omega t by 2 with its complex conjugate as iota omega t by 2, we will have it equal to 1. So what we will be left with is 1 by root 2 whole square. So that will be 1 by 2 as it's expected. And the probability of spin down, which is SZ as, so in this case SZ is plus h bar by 2, and in this case the SZ is minus h bar by 2, right? So so what will be that? That will be spin down state, okay, then acting on the state psi of t mod whole square. So that's going to be 1 by under root 2 e to the power of I omega t by 2 mod of whole square. As expected, we will again get 1 by root 2 whole square. So that is equal to 1 by 2. So what do we conclude from here? Is that that the probabilities of measuring spin up and spin down along the z-axis, these probabilities are always equal to 1 by 2. They're always equal to 1 by 2. Independent of time, see, there's no dependence of time. But at the same time, if we measured the x-axis, we measured it along the x-axis, the probabilities would oscillate. They will oscillate due to the precession of spin around z-axis. So that's a point. I mean, if we measure these probabilities along x-axis, these probabilities will cause oscillations, and these oscillations will be due to the precession of the spin around the z-axis. So we can conclude it by saying that electrons spin, what it does, it precesses around z-axis at Larmor frequency. But if we measure along z-axis, if we measure it along z, then the probabilities are 1 by half. But if we measure it away from z, then there these probabilities would oscillate, and they will oscillate because of what we call as Larmor's frequency. So now after this, let's go a little bit more ahead in this discussion, and let's try to analyze spin in a rotating magnetic field. Let's try to analyze this. Now, if we have spin in a rotating magnetic field, and how will we analyze the spin, and what will be the outcomes? Now what we have is a situation in which we have an electron, and this electron is placed in magnetic field at some time, say b of t, that rotates. Now this magnetic field is rotating. It's rotating magnetic field around the z-axis, and this magnetic field, let us assume that it has a frequency. It has a frequency equal to gamma initially. Its initial frequency is gamma. Now the electron's spin is aligned along the z direction. Now, what is the probability of finding the electron in the down state after some time? Say after time equal to t. Now, in order to solve this problem, in order to understand this problem, we take into account the time-dependent magnetic field. Now, if I write down the time-dependent magnetic field as b of t, it's going to be b naught of cos gamma t, okay, I plus sine gamma t and j. This is I cap and j cap. So this is the time-dependent magnetic field. Okay. Now moving on from here, the initial state, the initial spin state is aligned along this z-axis, and if I write down that initial state as psi of 0, as spin up. Now, what we have? We have this initial state as psi of 0, and this psi of 0 is represented by the spin-up state. Now, solving this problem, at least analytically, what it requires using the rotating wave approximation. It needs a rotating wave approximation, or solving the time dependent Schrodinger's equation numerically. But the key result is that the probability of the transition to the spin down state, it depends on the resonance. I mean, probability of transition probability of transition to the spin down state it depends on resonance. There's a condition that we call as resonance condition between the rotation frequency. So what's my rotation frequency? Rotation frequency, that's omega, and the Larmor frequency. And what's Larmor frequency? That is omega. This is rotation frequency and this is Larmor frequency. Now, the point is that if this rotational frequency gamma is equal to the Larmor frequency, is nearly equal to the Larmor frequency, there's a high probability of flipping the spin. Now, this flipping of spin is a point of contention. Now, when this omega is equal to, and this both omegas, I'll call this capital omega. Okay, so when this omega is equal to, when rotational frequency is equal to the Larmor's frequency, the spin will undergo oscillations, and we call those oscillations as Rabi oscillations. Rabi oscillations. Between spin up and spin down states, and the probability of finding the electron in the spin down state that we have been talking about at the time t is governed by, say, p, probability of finding this this spin in the down state is equal to sine square of gamma b naught of t divided by 2. So what am I trying to tell here? I don't know. Okay, let me go back. What am I trying to tell is that when we have the magnetic field and when the magnetic field rotates, when you have the rotation of the magnetic field at Larmor frequency, the electron's spin will oscillate between spin up and spin down states, with the probability of finding the electron in the spin down state oscillating as the function of time. So there's no absoluteness over here. There is an oscillation that's linked with the probability of finding that electron in the spin down state at that time. So all of these examples that I have taken here, the motivation was basically to demonstrate some of the key features of spin half systems. And such as superposition measurement, superposition, then the measurement of probabilities, and the interaction of spin with magnetic field. Then spin dynamics plays a crucial role in many areas of physics, including quantum computing, nuclear magnetic resonance, what is also called as NMR, and electron spin resonance, what's called as ESR. So with this, I would like to stop this discussion.